Welcome to another installment of the University of Alberta Geotechnical Graduate Student Seminars. Not much in terms of announcements today, but with people starting to focus on finals, I just want to wish everyone good luck and remind everyone that taking breaks to recharge your batteries is not only important for your cognitive retention, but for your mental health as well. So please take care of yourselves during these stressful times. Today we have a double presentation from Dr. Parisa Abdulrazagh, who is currently a postdoctoral fellow at the Canadian Rail Research Laboratory. Parisa completed her PhD in Road and Transportation Engineering at the University of Tehran. Parisa then joined Carl as a PhD visiting scholar in 2014, where she has led research in multiple railway condition monitoring and evaluation projects, specializing in big data analytics and autonomous techniques. Parisa is also a lecturer on non-destructive testing in pavement structures at Tehran University, has served on the Canadian Standard Association Technical Committee for Buried Structures since 2011, has published a book and more than 20 articles, has 2 beautiful children, and even has a black belt in Kyokushin karate, so don't mess with her. Today, Parisa will be giving us 2 presentations. The first will touch on the development of autonomous rail surface roughness evaluation method using axle box accelerations of in-service railcars. With increases in axle loads and operational speeds, the rail industry requires new techniques to assess the ride quality of the track to continue safe operations. This research presents a new technique using onboard accelerometers installed on Via Rail's passenger cars. This non-intrusive method allows for active monitoring of ride quality and will help save on maintenance costs. The second presentation will touch on the geotechnical considerations in the design and construction of buried structures. Specifically, this talk will touch on the soil steel buried structures and how to design and construct based on the CSA guidelines against things like structural buckling due to inadequate depth of soil or problematic soil materials. Please join me in welcoming Parisa.
Thank you very much, Kevin. Hello, everyone. Thank you for making some time to join my presentation today. I will be presenting about 2 topics today. One is about a part of my postdoctoral research on development of an autonomous technique to evaluate the condition of a railway track from accelerations. And the second presentation is about the geotechnical considerations in design and construction of buried structures based on CSA standard. I will be presenting around 20 minutes for each, so please stay tuned with me for both topics. Before jumping to my presentations, I would like to share with you part of my journey during my professional career. During my undergraduate studies, I took 2 summer internships in a construction company, which at that time, they were the contractor for subway light rail transit in my hometown. It was a live civil engineering school for me, which I learned all about the cost estimation, scheduling, all construction process and challenges of cut and cover, tunnels, retaining walls, the construction and building of the railway station, and also the tracks. So it was a mass construction project and so exciting. After I graduated from my bachelor, I started a position in a startup company. I had the opportunity to highly contribute to promoting the Canadian technology of design and construction of long span soil steel structures in Middle East for the first time. As part of a team, it was so inspiring for me to start seeing the picture of these structures on a CSPI book and making that picture as real projects. I continued my master in this field and published the outcome of my academic and industry experience as a book and more than 10 journal and conference articles in this field. At that time, I organized short courses in this field at 2 of the most top-ranked universities in Iran. I invited Dr. Bakht from Canada as a keynote speaker who was the technical chair for buried structures in CSA at that time. He was impressed with the work of our team and my contribution in this field, so he invited me to join as a technical member of buried structures subcommittee. And it is my honor to serve since 2011. Dr. Bacht and his colleague, Dr. Mufti, might some of you be familiar with them, are the pioneers in structural health monitoring. And it sparked the idea of applying the concept of health condition monitoring for railway tracks as a topic for my PhD thesis. I was developing a falling weight test during my PhD research, and I learned that Canadian Rail Research Laboratory at the University of Alberta are using an adapted falling weight develometer for sea and rail tracks. So I contacted Dr. Henry and he invited me to run analysis on their datasets. So I joined GFA as a visiting PhD scholar for 8 months in 2014. After completing my PhD in Iran, I joined the amazing team of UFA as postdoctoral fellow in 2018, and we run lots of field monitorings, and we are working as a team to run some of the field experiments. And I'm proud to make all this journey, especially in the recent 5 years, with my son, Daniel, and my daughter, Nika. Okay, starting with our first presentation topic, the development of an autonomous technique to evaluate the track condition from accelerations. The two objectives of this research is to evaluate the effect of track geometry and track features on the passenger's ride experience using onboard accelerometers, and to develop an autonomous technique to use accelerations measured on the axle box of in-service rail cars to evaluate track geometry conditions. And all of this research was how we analyzed the vibrations collected by sensors. Our everyday life is full of vibration. Our children enjoy the adventure of walking on a suspension bridge or riding on a swing. But when these vibrations are mixed, get random at different directions, they make us motion sickness. This is something we definitely don't want to experience when riding a train, or we don't want a coffee spill on us. What we do is to install sensors to record vibrations. Therefore, a service passenger rail car was instrumented with GPS and accelerometers, each measuring the acceleration in a specific direction. The accelerometers were installed under the car body, a bogie, which is a suspension system between car body and wheels, and on the axle box of the wheel. In parallel to this research, I led a research team in collaboration with NRC to record the accelerations using a free MATLAB mobile app installed on 8 smartphones, which were replaced on the seat and on the floor of rail cars. The accelerations and coordinates were recorded in real time. The data were collected from both ends cars and two middle cars in 2-day run experiment. Then I used different filters to extract vibrations that human is more sensitive to, which we call ride experience. According to ISO 2631 standard, ride quality is the level of vibration felt by passengers. In this research, I first calculated the combination of weighted accelerations in 3 directions, which is defined as AV or running RMS, as can be seen mainly at the location of track features, such as grade crossings, bridges, and culverts. Fairly uncomfortable vibrations were measured at that section of track. The calculated ride quality was mapped along the study track for two purposes. First, to indicate these locations for VRL to consider the upgrade these track assets indicated with red spots if the operating speed will be increased in the future. Second, to investigate whether the location of these track assets coincide with organic deposits which are shown in green, and if fairly uncomfortable vibrations are attributed to a stiffness transition in subgrade, or if it is attributed to a structural stiffness transition. Using the collected acceleration from axle box accelerometers, I developed an autonomous technique which makes it possible to evaluate track condition more frequent car is traversing the railway track. Track geometry condition is an important measure to ensure the safe operation of rail lines. One measure to this is track roughness. Track geometry condition of track is usually inspected by light or heavy track geometry inspection cars twice or three times annually, depending on the class of railway. Due to increased axle loads and operational speeds in recent decades, track geometry is deteriorating at a faster rate. As such, there is a need to inspect the track more frequently. Thanks God, this track is not in any of Canadian Railway. I just brought it to show a visible roughness. Track roughness means where the vertical and horizontal alignment of track are deviated from their designed position. Track profile has different components. Waviness, which is attributed to stiffness and long wave geometry variations, and short wave roughness, which are attributed to rate surface corrugations or squats. The key to this research was to use appropriate filter to cut off unwanted vibration components in this study, such as vibrations due to suspension system, rail surface corrugations, and stiffness variations, and just focus on the changes of the geometry. I have filtered the waviness attributed to those unwanted components based on Gaussian filter recommended by ISO 11562. And they do have like an open source Gaussian filter, which I've used in my calculation. This figure shows that after filtering the major track surface, both the vertical accelerations and the surface recorded by track inspections, track geometry inspections cars are having the same wavelength, dominant wavelength at 2 and 6 meter. After feeling confident that I'm dealing with the type of acceleration data sets that has a strong characteristics of the surface geometry, I have calculated the vertical track profile from double integration of axle box accelerations. First, I have eliminated the nonlinear trend of acceleration signals by fitting a second order polynomial, and then subtract it and use it the best fit least square method using Cramer's rule. And I have repeated twice to finally calculate the displacements. And also I have corrected the displacement for baseline offsets. Figure C shows part of the result of velocity and displacement using single and double integration after applying nonlinear deterrent and baseline corrections. Another key point to this study was that double integration of acceleration does not result in absolute rail vertical profile, but rather a relative, like two sequential displacements are subtracted. Those are like relative displacements. Whereas the track geometry inspection car measures absolute variations of track profile from its designed level. Therefore, I had to calculate the relative surface roughness as a root mean square, in which I consider the relative displacements of the rail surface as an input to the formula. In the third step, I compared the calculated vertical track profile and those calculated roughness from the measured rail surface by a geometry inspection car. Figure A to C shows both surface and rail vertical profile roughness calculated by computing the root mean square level of the inputs over every 100 meter, and are compared for three example sections that which you can see in these three figures. So the question is that why 100 meter? So from the statistical point of view, for having a sufficient statistical sample number to represent of the population, which represents that behavior or variation or changes, we need like enough number of data. Considering of that, 100 meter was like the longest length to fulfill the minimum required samples for this study. Also, I have made a sensitivity study on over different lengths, and 10 meter could be also the smallest length because it should cover the wavelength of 6 meter. So that's why I have calculated both for 10 meter and 100 meter, which usually is used for like maintenance based calculations. These two figures shows the regression analysis between the two surface and rail vertical profile moving RMS values. The coefficient of determination and the value of a standard error for the window length of 10 meter and 100 meter show the strong correlation between the calculated rail surface and those measured. The concluding remark is that the results of the developed technique is promising to calculate the roughness track geometry from Excel box acceleration data, and track surface roughness in this study that we have seen that 2 and 6 meter are the dominant frequency, the 10 meter is the minimum length, sufficient length to capture the texture of variation of rail surface profile, and also like the 100 meter also again in this study was the largest window size that we need appropriate and enough sample to make any calculations. The outcome of this research can be used by the rail industry to identify track locations which might be more susceptible to degradation and which their upgrades will be significantly improve the ride quality of track. The result of this research also helps to reduce the consequence of high dynamic impacts on bridges, switches, and therefore safe maintenance costs for these two railway assets, as well as the cost of suspension system. These two are related to the ride quality study. And so for the roughness part of the study, the methodology developed in this research makes it possible to actively and non-intrusively assess the rail surface roughness in an inexpensive way and on a daily basis directly from the data measured by Excel box accelerometers. which are mounted on service rail cars. The developed methodology can be used as a complementary technique to light and heavy track geometry inspections to proactively identify rough surface conditions prior to formation of any major rail surface defects. And here are some of the major references. Thank you very much for listening to this presentation. And I would be happy to answer questions for 5 minutes before moving to second presentation. Thank you.
All right, thank you for your first part presentation. I didn't realize you have a second part. And Dr. Parisa, and so far I haven't seen any people asking questions yet, but let me ask you one question. So to calculate the roughness of the railway, did you only use the one axis of your accelerometer data, like the vertical axis? I mean, how would the other axis, like say horizontal vibrations or the other vibrations would matter in your roughness calculation?
So about the roughness, I've just focused on surface or variation of the vertical profile. So I've just used like one direction set of the data, vertical direction of the data. And actually there were like 4 axles instrumented in a rail car. So prior of that, I have made a study to see, for example, if left, right, or right side, or for example, the direction of the travel, like which end could be like have an effect on the measured data. And it was, the calculated roughness was independent of the sides or like the end of the car. So independent of the location of the axle.
Okay, thank you.
Quite welcome.
So I guess no, yeah, go ahead.
Yeah. So if there is no other question, I will move to second presentation.
Sure.
The second presentation is about the geotechnical consideration in the design and construction of buried structures based on CSA standard. Canadian Standard Association regulate the design and construction of buried structures through Canadian Highway Bridge Design Code Section 7. The section specifies requirements for the analysis and design of soil metal structures, metal box structures, and reinforced concrete structures. In this presentation, I will focus only on the design and construction requirement of soil metal and metal box structures. For sure, you have seen the conduits for drainage and sewage in the city and so out of city, road bridges over river streams, and overpasses for wildlife in Banff National Park. CHBDC Section 7 covers the regulation for the design and construction of all these soil steel structures with variety of span lengths and structural shapes. The history of this structure backs to 1886, where an engineer named Watson, who took the idea of corrugated plates from the corrugated paper wraps of bottle and invented the pipes made of metal corrugated plates. The advantage of corrugated plate is that the area and moment of inertia of the section is doubled over the same length, which allows for bearing significant larger stress. For example, if you consider like a sheet of paper, it's flat, you can see the deformation. But if it's corrugated, like you can see, like there is least deformation and like can very like, significant larger of loads. However, the conduit might undergo excessive compression, and side pressure can help to increase the compression strength of the conduit. These side pressure are attained by layered compaction of soil around the corrugated steel plate structure. Canadian Highway Bridge Design Code have defined specifications to prevent plastic hinge and deformation under service load and under construction load. Part of these specifications are related to geotechnical considerations to prevent any soil capacity and tension failure by defining minimum height of soil cover, metal requirements, and adequate compaction and right practice of placement of materials, which in turn prevents local buckling and connection failures. The related clauses are listed in this slide that you might be interested to check. Today, I don't have intention to go through the details or formulas. I only touch base some of the concepts of some of the listed clauses. The first clause is the minimum height of soil cover for service structures. The minimum height of cover means the height of soil cover between road surface and the peak of corrugated plate. Usually, there is an optimum height of soil cover, which minimizes the pressure from live load while maintaining the least dead load due to weight of soil. The minimum height of soil cover helps to avoid buckling of conduit wall by controlling the combination of bending moment and axial thrust both during the construction and under service loads. At least 30 centimeter soil covers should be dumped over the crown of the structure to allow for traveling the light construction equipment. Another important aspect of the geotechnical considerations is the extent of engineered backfill on both sides of the structure. Each zone have minimum requirement for soil materials. A non-frost susceptible soil materials should be compacted at least 1 meter from both sides of the structure. Non-frost susceptible soils immediate beside the metal walls are of type of well-graded gravel or sands with a minimum 75 millimeter particle size and less than 50% passing the 0.15 millimeter sieve and less than 10% passing the 0.075 millimeter sieve with plasticity index less than 6%. Following these specifications can reduce significantly the road surface and railway track issues during winter due to forming of ice lenses in poor unengineered soil. During the placement and compaction of soil materials on both sides of the structure, minimum space of 1 meter should be maintained between the steel walls and the heavy construction equipment that we consider are greater than 10 tons. Also, the construction equipment should move parallel along the structure and avoid any perpendicular movements. The placement of soil material should be even on both sides of the structure with maximum difference of 1 layer. The maximum loose thickness of each layer of material is 25 centimeter. And the engineered backfill immediate beside the structure in zone 1 should be compacted 85 to 100% standard fracture density to prevent the buckling of the crown during the construction. When the backfall reaches approximately the mid height of the structure, dumping of soil materials on top of the crown might be required. As you can see in this picture, the soil materials based on the beside the structure are compacted only by light compaction equipment. The concluding remarks of this presentation is that following the geotechnical considerations in design and construction of buried structure prevents a structural buckling due to shear or tension failure in the soil cover and backfill, and prevents a rough surface of road pavements and railway tracks crossing over the buried structures we can see in many places, reduce the maintenance cost of roads, highways, and rail lines. And here are some of the major references. Thank you again for joining these two presentations, and I would be happy to answer any questions. Thank you.
All right, that was a quick presentation. Thank you again, Dr. Parisa. Now let's waiting for questions. And not sure if anyone has any question about your second presentation. If not, probably we should just end this.
Can I ask a question?
Oh, here you go.
I have a question about the actually cost saving in the maintenance progress of this kind of a structure, and also about some safety issues. I mean, safety boundaries for this kind of a structure, because actually I could not find anything that regard to the safety problem of this buried bridge, but maybe there was some consideration in this regard. So that would be so good if Dr. Abdulrazagh could help us in these things. Thank you.
Answering to both of your questions are like based on following the guidelines of CHBDCs and complementary notes again by CSA standard. So they have like specifications based also on the durability. So if, like, for example, the coatings, first of all, like if they're used for the rivers or streams, they always calculate the amount of the corrosion or like the pH level of the water, and for example, the particle size. So all of these are considered in the durability design. So first, what we do is we consider the required thickness based on the service life of the structure. For example, there is a reduction amount on the countings. We calculate based on the corrosion levels, how many micromillimeter is reduced. And then we add it to the minimum structural thickness required for these structures and the conduit walls. So like there is no, so all of these helps to, if like all of these guidelines are followed, there is no like maintenance requirements. Sometimes might be there are debris, which I believe also there are for any other structures, for concretes too. That's specifically for their rivers might be need to have cleaned some debris. So it's not specifically related to these structures. And again, all of these requirements are based on the ultimate limited state design and the safety factor of design for the buckling, the compression, the connections failure. So there are like added um, design like factors to the load, at the same time decreased factors for the strength of the wall, conduit wall, and also the soil based on the level of compactions and type of material. For all of them are considered in the process of design and construction. So like actually there is no safety issues. And that's why we are using like the plates material all stamped by CSA, and also this committee are formed to make sure that both the design and if like the contractor follows the constructions steps, there won't be like no like significant maintenance or not at all any safety issue concerns. I hope I could answer your question.
Yeah, perfect. Thanks for the great topics and for the presentation. Many thanks.
Thank you very much. Quite welcome.
All right. Without any other questions coming up, so I would like to say thank you again to Dr. Parisa for this presentation, and I just hope everyone would enjoy this presentation, and I look forward to everyone to coming to our last seminar in next week. That I would like to say have a good day and see you next time.
Thank you very much, and thanks again for joining the presentation today. Bye.
Bye.